Hello student, welcome to the lecture. Now in this lecture we are going to discuss the F2 molecule. So this may be considered as we know that the F2 molecule is formed by the combination of one F atom and another F atom to form the F2 molecule, and the electronic configuration of F fluorine, that is 1s2, 2s2, 2p5. So there is a 5 electrons in 2p orbital. So in that there is a 1s orbital does not take part in bonding, and 2p molecules, actually 2s orbital doesn't take part in bonding, just only 2p orbital are take part in bonding actually. AOS, that is MOS, and this is again AOS. So now what is about the 2p orbital? That is, we know that there is a 6 electron. So here sigma 2px, this is then sigma 2py, this is again sigma 2pz. Here also this is the star 2p, sigma 2px, that is an antibonding molecular orbital which is an empty, and that is 2py antibonding, that is sigma 2py, that is an antibonding one. Here again that is orbital. This is first fluorine, this is the second molecule, and this is the formation of F1. So that is sigma 2s2, sigma 2s2, and that is sigma 2py, 2 sigma 2pz, 2 sigma 2px2. So here also there is a pi 2py, pi 2pz, pi 2px, not x here. There is antibonding pi 2p y orbital, that is pi 2pz orbital. So while writing the electronic configuration of F2 molecule, the letter K is used for each one as orbital for while writing the molecular electronic configuration of F2 molecule. Bond order. That is diamagnetic. So here for F2 molecule, the first 1s orbital does not take part in bonding. So we cannot write here. Instead of that, we are taking the 2K, that is means 1s for 1 fluorine, means there is a 1s for 2 fluorine. So that's why we written the letter K 2 times here. Now here there is a 2 electrons in 2s orbital, whereas in antibonding orbital there is only 2 electrons. Remaining 14 electrons will be occupied by Hund's and F2 principles in the respective atomic orbitals of these F2 atoms. Now this is all about here. In 2p orbital, that is a 2 electron in sigma 2px orbital, as like in sigma 2px orbital there is a no electron which is an empty one. After that the 2 electrons simultaneously 2 electrons means 4 electrons will be enter into py and to pz orbital of fluorine, and here again antibonding orbital there will be again the same 4 electrons in 2 electrons into p while antibonding and 2 electrons into p pi to pz antibonding molecular orbital will be occupied. So this is all about the F2 molecule or the MO energy level diagram for F2 molecule. Now we will discuss the next one. For heteronuclear diatomic molecule, is the homonuclear diatomic molecule. The same principle, that is a linear combination atomic principle, is also applied for, is the same for the heteronuclear diatomic molecule. But the only difference is that for homonuclear diatomic molecule, we can use molecule, that is we can use that psi is equal to phi A minus phi B here. Likewise for heteronuclear diatomic molecule, that is phi means that is a wave function of AB is equal to phi A phi B, that is lambda is a mixing coefficient and which is not equal to 1. So here the lambda is a mixing coefficient which is not equal to, and for the combining atom there will be some condition, as we know that the atomic orbital overlap similar extent, means that they have equal energy. There is a maximum overlap between the atomic orbital. So these are the all criteria orbitals. So these are the all criteria for combining orbitals. Likewise homonuclear diatomic molecule, also heteronuclear diatomic molecules can combine into form and molecular orbital. So let's discuss the heteronuclear diatomic molecule. In the first example, that is NO molecule. A nitrogen and oxygen molecule combined. To form NO molecule. Electron configuration 1s2, 2s2, 2p3, whereas oxygen is 1s2, 2s2, 2p, then plus O. There will be the total 17 electrons for NO, that is 7 plus 8, total 15 electrons. In nitrogen and in oxygen, the inner 1s2 orbital does not take part in bonding. Just bonding takes place with 2s and 2p orbital of nitrogen and oxygen atom respectively. So let's discuss the MO energy level diagram. So this is the MO energy level diagram for NO molecule. Here that is a nitrogen molecule, this is an oxygen, and in middle that is a formation of NO molecule. That is an 2s orbital of this respective nitrogen and oxygen atom. So here that is 2 molecules in 2s orbital of bonding, and 2 electrons are sigma 2s orbital of antibonding molecular orbital. Here that is an oxygen, for there is also 2 electron, and for nitrogen in 2s orbital, atomic orbital of nitrogen contain 2 electron. Now what about the 2p orbital of nitrogen and 2p orbital of oxygen atom here? So here if you see that the sigma 2px orbital contain 2 electron which is in bonding 1. Also there is a 2 pi and 2pz orbital contain 2 electron each. Now in antibonding molecular orbital, that is only 1 electron in pi 2py orbital of NO molecule, and there is a 2 electrons, there is a 2 orbitals are empty, that is a pi star 2pz orbital, and sigma 2px orbital of NO atom is empty. So what is about the molecular electronic configuration of this NO molecule? So we can write here. So that is electronic configuration, that is Kk sigma 2s 2 sigma 2s 6, that is 2 pi 2p and pi 2p y antibonding 1 orbital. So here there is one unpaired electron in 2py orbital of NO molecule. So the bond order can be calculated as bond order equal to half into number of bonding and number of antibonding, that is in through the bonding molecule. So the bond order is 2.5. Means that this is a paramagnetic. So this is all about the MO energy level diagram for NO. Now let's discuss the CO molecule, that is a carbon monoxide. It is also a heteronuclear diatomic molecule which have in carbon has an electronic configuration, that is 1s2, 2s2, 2p2, whereas oxygen, that is 1s2, 2s2, 2p4. So the total electron for carbon and oxygen, that is 2 plus 6, that is 8 electrons take part in bonding formation. Actually this 1s2 orbital doesn't take part in bonding, so that's why only 2 orbital, that is 2s and 2p orbital can take part in bonding. So let's discuss the MO energy level diagram for that. That is energy. Yes. Two electrons in each, that is sigma 2s antibonding molecular orbital, that is 2s again. So this is an AO atomic orbital of carbon and atomic orbital of oxygen atom. Now, what is about the 2p orbital? Pi 2px orbital. This is the pi 2py, pi 2pz, antibonding molecular orbital. Here also pi 2px, antibonding molecular orbital. So here is 2p, here also 2p. So this is a formation of carbon molecule. This is an oxygen one, and this is a CO molecule. So if you see the electrons filling, that is 2s orbital. In antibonding molecular orbital of 2s, there is a 2 electron in carbon and 2 electron in oxygen. Also in bonding and antibonding containing 2 electron each. Now in in 2p orbital, that is in pi 2p1 and pi 2pz orbital contain 2 electrons, and here also pi 2px orbital contain electrons, whereas the pi 2py, pi 2pz and pi 2px antibonding molecular orbitals are empty in CO formation. Now what about the molecular electronic configuration? As we know that the molecular electronic configuration of CO sigma 2s 2 step, then pi 2py 2, pi 2pz 2 and pi 2px 2 orbital here. Again for one s of this 2 carbon and oxygen respectively, we can use the letter K for 2 times sigma 2px. Here also that is sigma 2px. This is also a sigma 2px orbital. So bond order of NO molecule, that is half into number of bonding, that is, and number of anti electrons. So here the total, that is 3. The bond order is a 3 for carbon monoxide, that is a CO molecule. So bond order is nothing but the number of bond present to form a molecule. Means that there is a 3 bond in CO molecule, that is a stable one, and the bond length is considerably decreased. So due to the bond length, decrease in bond length increases the bond strength, means that the bond increases the bond energy. So here this is a CO molecule, is a stable one having the bond order 3. So now we will discuss the next molecule, that is an HF molecule.